Hi, my name is Jogo. I'll be presenting a work titled A Graph Transformation System Formalism for Correctness of Transactional Memory Algorithms. Here's a summary of this presentation. Introduction. One of the main themes of this work is transactional memory, and the definition of transactional memory, or TM, says that it provides a high-level concurrency control abstraction. Some of the benefits of using TM over locked-based systems are composability, scalability, robustness, productivity. And there are three main implementations of TM: software, hardware, and hybrid, and we focus specifically on software. One of the most important parts of the definition of TM is the correctness criteria. It allows development of programs and reasoning about correctness of these programs. Some of the correctness criteria proposed, which rely on the concept of history, are weakest reasonable condition, virtual world consistency, and opacity. We used the correctness criteria called opacity. Recent works on formal definitions of TM focuses on consistency conditions, fault tolerance, and scalability. The study of correctness criteria fits into consistency conditions. Here's the definition of history and opacity. History are a sequence of actions. They happened concurrently, and history is said to be final because the actions already happened. And here's a quick example of three transactions executing reads and writes to variables in the shared memory. And the definition of opacity says that all operations performed by every committed transaction appear as if they happened at some single indivisible point during the transaction lifetime. Also, no operation performed by any aborted transaction is ever visible to other transactions, including live ones. Live transactions are transactions that haven't either aborted or committed. And finally, every transaction always observes a consistent state of the system, which is the main point, the consistent state. The other main theme of this work is graph transformation system. And the definition of GTS says that they are flexible formalism for specification of complex systems. Applications that would use GTS involve many types of elements with different relations or are data-driven. In a GTS, the states are modeled by graphs and rewriting rules, and you change states using these rules. Examples of systems that use GTS are reactive systems, protocol for distributed and mobile systems, and biological systems, etc. Here's a formalism of GTS. It says that graph G is a tuple with a list of vertices, a list of edges, and two functions, sources and targets. There's also the notion of a typed graph, where it's applied to every graph in the system. It basically says that how a graph should be constructed. What is the correct way of constructing a graph? We also use the single push-out approach as opposed to the double push-out. In the single push-out, it says that rules are partial morphisms. Transformations happen by creating or deleting items in these graphs, and there's a left and a right side to the production rule, where the left side is what I'm going to use for pattern match, and the right side is the result of me transforming the state. Here's the syntax for the tool that we use to create graph transformation systems. This tool puts the left and right side of the production rule together, so the coloring helps identify each action. The black objects are objects that are going to remain unchanged when the rule is applied. Blue objects are going to be deleted. The red objects must not exist for the pattern match to work, and the green objects are going to be created. Now for the proposal of this work. The main objective is to define a methodology to formalize TM algorithms using graph transformation systems, and to observe the property of opacity on all histories through the use of computation tree logic, or CTL. The motivations for this work is to introduce a new method for proof of correctness of TM algorithms, and to explore graph characterizations of TM properties. Some of the main contributions that we found are generic formalization of TM algorithms, and an approach that is capable of being extended for new graph characterizations, and also a proof of correctness of existing TM algorithms that we demonstrated. The methodology is split into 3 steps: the translation to the GTS, generating all histories, and correctness criterion test. In the first step, we define the initial state and the type graph, and we translate all the TM procedures into production rules. In the second step, we generate all histories using a labeled transition system. And the third step, we test for the correctness criteria, in this case, opacity, using a computation tree logic formula. Now for the translation. Here's an example of an initial state that we can use. Here we have 3 transactions with read and write operations. What we are looking for is conflict, so all 3 transactions use the same variable x. And here is how these 3 transactions would look in a graph manner. We can see that an object represents the entire operation, and the sequence is represented by an edge called next. We also store the unique identifier for each transaction to keep track of what was executed and what was not. For the initial state, we have the transactions that are going to be executed and also a couple of global items that are required depending on what the algorithm needs. Obviously, we are using shared memory, so that's going to be global, but also a list representing the history of all the actions that were executed until now, maybe a list of active transactions or a global clock. That will all depend on the algorithm itself. New states on this system is generated by applying production rules, and the type graph makes sure that every new state generated are constructed correctly. Here is an example of a type graph. We have a few global objects like a list of active transactions, shared memory, history, etc. And this is a feature of Groove itself, where we can represent inheritance, just to simplify a little bit the demonstration of these different objects that have the same relationship. The TM procedures are a very important part of the algorithm. A couple of examples of procedures are init, read, write, commit, abort, maybe an extra function for verification, for a clock, whatever the algorithm needs. But these procedures can be lazy or eager in both versioning and conflict detection, which are characteristics of the algorithm itself. And this reflects in the translation to the GTS, so it also needs to be kept in mind. Here's an example of an eager versioning read operation. This operation will take the target of the current operation read and match to its corresponding object in the shared memory, save the value in a new item at the end of the history, and move the operation to the next in the sequence of operations from the transaction. Now talking about the histories. Production rules act as procedures, and applying a rule adds an item to the history. Because the transactions will execute concurrently, there is a non-determinism of which production rule to apply. So if 2 or more production rules can be applied at the same time, the LTS, or the label transition system that I'm generating, will branch into 2 or more paths, representing each different execution order. Different histories can be seen at the leaves of this tree-like graph, and when there's no more execution, the histories will be completed. Here's a quick explanation of how the LTS works. Each node here represents a current state of the system, and each edge connecting states represents a production rule that I apply changing the current state. What is most important here is the history being generated. Each production rule will add an item to the history, so the histories order are different, and this is what I want to evaluate for correctness later on. The different order of executions will change if the property of opacity is true or not. And here is how it looks in the Groove tool. All the way at the top, I have the initial state with all the transactions at the beginning, and the history is empty. And at the bottom, I have states where no production rules can be applied anymore, so these histories are complete. All the transactions have been executed. And the path following down to the leaves represents different order of executions from the transactions. Now for the test of correctness. The correctness criterion used is the graph representation of opacity proposed by Gehawi. In this definition, from a history, I can create a conflict graph that represents the conflict between transactions. The conflicts are real-time, reads from, write before write, and read before write. Here's an example of a conflict graph created in a Groove tool. We can see 4 transactions with identifiers 0, 1, 2, and 3. Technically, the transaction 0 is present in every history, and its only purpose is to initiate the variables with the value 0. So in this history, we had 3 transactions that executed writes and reads in different variables, and the conflict relationships can be seen in the edges between these nodes. The idea of the graph characterization of opacity as a correctness criterion is to observe the presence of or not of cycles in this conflict graph. So if the history generates a conflict graph that is acyclic, that means that history was opaque. So what we want is to test every history that the algorithm generates to see if their conflict graphs are cyclic or not. And we do that by using a CTL property in matching a graph condition that we call cyclic. And the conclusion that we will get is that if the algorithm only generates conflict graphs that are acyclic, that means the algorithm only generates opaque histories. So the algorithm is opaque. And the conclusions: it is possible to make a formal definition of TM algorithms using GTS, where eager and lazy implementations of versioning and conflict detection are reflected in the production rules, and correctness is verified through the graph characterizations of opacity and a CTL formula. In this work, we extended a previous one that only dealt with one history at a time, but this time we managed to do it for the entire algorithm. For the case study, we managed to prove the opacity of an algorithm called CAPR+. Usually an algorithm makes a full rollback where the transaction aborts. It goes back all the way to the beginning, but this algorithm in specific does a partial rollback. So it's a bit more complex than usual. For the next steps, we want to create GTSs for other algorithms like the TL2, which has been proven to be opaque, the STM Haskell, which has been proven to not be opaque, and maybe a newer algorithm as an extra. We also want to explore other TM correctness conditions. We used graph characterization of opacity because it has already been introduced, so it was an easy choice. We want to see if other properties can also be created into graph characterizations. That is all. Thank you.